day. And the goal of the project was really to put something together for perspectives to take away. So that ended up being a puzzle. The puzzle pieces we ended up doing were modeled in Creo, and then we cut them out in a wire EDM in the machine shop that we have in Hoyt. We then took the puzzle pieces and designed around what we were going to do with those for the rest of the robot. So we ended up taking those and they're placed in that rotary feeder on the side, and that's rotated in as the puzzle is put into place for the robot to assemble. We then have the robot scan each piece. So there's a vision system on it with a little camera. It knows what the piece looks like and the way it's supposed to be oriented. And it basically looks at the piece and identifies which way it's pointing, which side is which, and identifies what the piece is. It then computes the correct order and orientation, and then it's placed into the puzzle in the correct order that it's supposed to be. So, if piece one's over here, puts it in the puzzle and starts from there. The robot then returns to the home position, can rotate the rotary feeder out and take the puzzle out of it, completed as it was when it's supposed to be. So a couple features of the project we have a custom-made rotary feeder, which you can see right there. We have a human-machine interface, software on it that we installed to kind of have a touchscreen system. We have a vision system, which Ben will talk about. And then we have some safety aspects with it so the robot doesn't hurt anybody. And that includes the big safety cage you see there, which is made out of A20 Lexan, and a locking system on the cage just to make sure that nobody can get in there while the robot's operating. So we're going to have Clayton talk a little bit about some project aspects.
So some important design considerations we had to look at when we first started this project was we wanted this project to be a memorable giveaway for prospective students. Since our main goal is to attract more engineering students to Grove City through admitted student days, where lots of different students come through and are able to view our project, we wanted to make something nice to give out. So we decided on a movable puzzle. We wanted the project to be interactive. So by making it interactive, students would have a better aspect of what a senior design project can look like, and just take a lot more away from viewing this project than just sitting there watching a robot assemble something. So to make it interactive, we used an interactive display, which we'll talk a little more about later, and a manual rotational feeder. We also want to prioritize the safety of the onlooker. Since this project is being shown off on days where there's lots of people milling around, we wanted to keep people safe so no one would walk into the potential cell where the robot's working. So by doing this, to solve this, we put a safety cage around the robot using 8020 Lexan, and then also some other built-in systems to a robotic. We wanted to minimize the modifications to the teaching cell. This robot sits on the second floor of Hoyt for most of the year and is actually used in a class in the fall. And so we want to be able to have a project make minimal impact to the system in which the robot works on for that class. And so it easily detaches from the robot from the teaching cell with just a couple of bolts and can be disassembled onto different carts and taken down the Hoyt elevator or carried down the stairs if the piece is too large to fit in the elevator. And then this lastly brings us to, we wanted to prioritize movement between the buildings. Since this robot's on the second floor, it's difficult to get it through the Hoyt elevator since the Hoyt elevator is very limited. So we had to kind of design around the elevator for some aspects, but some aspects, like the safety frame, we couldn't lack on safety, and so we had to make the safety cage as large as it is, and so it has to be carried down the stairs. Once everything's down on the first floor of Hoyt, we can assemble it and move it between the buildings of where it needs to go to be demonstrated during those potential days. So this is our current iteration of our puzzle. The puzzle will be passed around. We have one which is just off the wire EDM, is where we make these, and then one which is in a wooden box, which is what potential students would receive upon viewing this project. So we went with a simple design that showcases both Grove City and mechanical engineering department. It consists of 6 interlocking pieces, with the final piece being the GCC shield, which is placed into the robot, which is placed into the puzzle last. So with the puzzle, we had a lot of design requirements with this. Since potential students could be handling this, we wanted to reduce sharp corners, so students would be cutting their hands on the project, on the puzzle, while they're handling it and putting the pieces onto the feeder system, or playing with the puzzle afterwards. So we reduced the sharp corners on the pieces, we wanted interlocking pieces because we wanted it to look like a puzzle, since one of the main draws is to make the project look good for potential students to be interested in our major. We have a grip width of 1.4 inches. This is the width our gripper can the maximum width our gripper can extend, and so we have to design around that with our pieces. So every piece where the robot grips it is designed to meet that specification. But some pieces actually have to be changed down in later design iterations of this puzzle to make that a little easier for the gripper to work with. All the interlocks, which is where the two kind of puzzle pieces connect together, are a width of 0.11 inches. This is the correct amount of width that we needed for the gripper to slide into these kind of pieces. So I'm talking about these pieces right here, basically, with the interlock. And then all our edges are tapered. So we actually tapered all our parts by 2 degrees. So even if the puzzle piece is placed incorrectly, just ever so slightly, it will slide into place in the end of the project. And then we wanted a close fit on the top surface, which doesn't really reflect well on this, but in some other pictures, you can see that you can barely see the lines and markings between the pieces. And this is because we have a tight tolerance of about 0.02 to 0.03 of an inch in between each piece. This tolerance just kind of demonstrates the precision that a robot can have to a potential student. So to make our puzzles, we had to come up with a couple fixtures. One of the main fixtures we had to design was a fixture for the wire EM. Since all our puzzles are being made in-house, and with such many type and design tolerances that we had for this puzzle, we came up with the best way to make these puzzles was on our wire EM. So to make the puzzles, we needed a fixture to hold the pieces of metal in the wire EM while it was more or less cutting them out. So the wire EM takes 2.5 hours to make one puzzle, where it takes 7 minutes to engrave 2 puzzles. This is because the wire EM takes a long time, but it's such a high precision process that it works well in our favor in the long run when it comes to assembling the puzzles. Lastly, we can also buy the material in bulk from discount metal places and cut it to the sizes that we need to fit within our wire EM. Our last piece that we had to make was our box manufacturing. This was more or less a plate that we needed to design to be able to continuously and precisely route out the top openings of our boxes that you can see in which the puzzle fits in that is being passed around. We can mount this to a table, and then using the plunger here, we can actually push the wooden box that is cut to size that we need into 3 locating pins, which puts in the right position that we can use a router to more or less mill out the pocket that we need for the puzzle to sit in. So now you can talk a little more about some other aspects of the project.
Some other really important aspects of our project was the grippers themselves, since this is how the robot interacts with the physical puzzle pieces. So we wanted our grippers to be really precise, and we wanted to minimize error between the robot and the actual puzzle piece. So we made them self-aligning. To do that, you can see that the left gripper piece in this picture is slightly rounded, because this goes into the rounded piece of the puzzle. That way it always locates, it doesn't really shift in the wrong direction, it always finds the middle. And this side is flat, and it's always located up against a flat side of the puzzle piece. And then this is attached to these 2 bolts here, which just go through threads on the grippers themselves, which make it really easy, really simple, and really fast to attach and detach them. That way it can be changed over to a new gripper set when necessary. Another important part of our project was the base plate, since this is how everything is attached to the robot. So we wanted the base plate to be very easy to move, and we wanted it to be positioned very accurately. We also wanted it to require minimal calibration to make everything simple and repeatable. We also wanted to use the current framing structure without having to damage or modify it. That way it could still be used just as easily for future Robotics 301 classes. A couple things we did as well was we used standard hole and thread sizes with a countersink to make it easy to attach pieces to the base plate. We also used a 2-inch square pattern. That way, if there are changes in the future, we already know the bolt pattern and we don't have to add bolts to it which makes the whole thing simpler since we could not actually manufacture this in our own shop due to size. We also used undersized holes, which we can put dowel pins in for locating without screws, and the outermost holes are actually offset for the positioning of the safety frame. We also had to widen the base plate because there was a clearance issue with the safety frame and 2 side flaps of the robot, so this eliminated that issue and eliminated a pinch point. We also used a slightly larger tap size than originally planned. We initially wanted to use 1/4 because it's readily available, but had to upsize to 5/16 18 because that was the smallest size available for our safety frame. That way everything was consistent. There are also 2 slots on the underside of the base plate here where you see the 2 holes, which are used to attach the base plate attachment. The base plate attachment itself is rather simple, but we had to break it up into 2 pieces to make it easier to manufacture in our own shop. You can see the 2 larger holes above use the current mounting on the front of the actual robot arm. That way we did not have to add any hardware to the base plate, to the robot's existing base plate. This is very repeatable as we use the 2 slots here to line up with the 2 slots on the underside of the base plate. So it always slides in the same spot and secures with 2 simple 1/4 bolts. And this is also small enough that it remains out of reach of the robot because of its own safety systems. So it can remain on the robot after our project is completed without interfering with future robotics classes.
Now, our project needed a way to introduce all 7 parts into the assembly cell without a human coming in contact with the robot. So that's where the rotary feeder comes in. Now, the rotary feeder is made out of 5 main parts: the top work surface, the acrylic circles, the Lexan large circle underneath, the top turntable, and the stationary bottom turntable. So as you can see here, this is the top work surface. So this is actually where the robot does all of the assembly. So right here, you would place all 7 of the pieces in each circle, with the smallest ones being on the outside and the shield being next to the actual assembly location. And this is where you would put the box. Now it actually has 2 work circles that the robot will be working on one, while the prospective student, the next one, is also putting their puzzle pieces here to keep the process flowing. Now this is bolted to the actual rest of the turntable itself. And then another part of it is there are acrylic circles and then the Lexan shield underneath. What those do is they allow light to come up through, so you have backlighting on the parts for the robot's vision system. And on the turntable, we needed a way for it to stay stationary when it needed to be and then move when it needed to move. So the top circle here is bolted to the large work surface that you saw, and the bottom part is bolted to the actual frame. So what we have here, these are ball nose spring plungers, which when a force is applied to them, they sink down in and can roll, and that's what the actual turntable rolled on. But we also had a locking pin on the top, just in case someone would try to move it while the robot is working, it would stay stationary.
So to talk about a little bit about the robot itself that we're using for this project, as you can see in the picture over there, this is a FANUC LRMA series robot. It's about the size of a human arm. It has 6 degrees of freedom. It has a max speed of about 4 meters per second linear direction, so that's pretty fast. And you can see by the black part over there on the end, that's the customizable tool head. That's what allows us to design and create our own grippers for whatever you need, and has many different applications. So there are 2 ways you can program this robot. First, we used last semester is the FANUC proprietary software called RoboGuide. It's simulation software that you can bring in a simulated robot and cell and bring in CAD models that you designed yourself. So that's what we did before we ordered any of our things. Before we got anything made, we brought things into this simulation to test whether or not they would fit together well, whether or not the robot would interact with them well. And you can see here, this bubble here is its kind of reach that you can program into it. And that was just a way for us to make sure that everything was going to work well and not waste money on the project. The second way to program this robot is by the Teach Pen. This is more of a direct method. This is attached directly to the robot's controller. It uses the FANUC TP programming language. The TP command structure is basically made up of 2 parts. The first part being a command, and the second part being a register. think of a register as more of a straight variable or definition. You can have a position register, a plain data register, and a command is just telling it what to do. So this command here is a joint movement, right here with the J, and this right here is a position register that we call home. It's the home position that the robot will always go back to. It's kind of like the default that we set. And again, over here, this is speed register. It is set to like a definition of what speed you want the robot to go to when executing that command. So this is a flowchart of the programming structure that we came up with for our different programs working together to build a puzzle. It starts out under one program that calls all the others called Senior Design. It then goes to the first program called Vision Circle Scan. This checks the model ID of all the pieces. It gets what pieces are in what circles, what's their location, and orientation. It then obtains their offset location and then calls select piece. This assigns a data register to each circle, and then we created a for loop that calls select circle, the next program, for each iteration for each piece. What select circle does is that it has a list of if statements, and it goes through, and it's like, okay, if this circle has this piece, what do I do with it? Where do I go with it? That's all previously defined by working with the robot ourselves. If the desired piece is in the order found in what circle, it calls the pick program. There's a unique pick program for each piece because we define where we want the piece to be put in the puzzle in what order. And so this three programs right here loop for every piece of the puzzle. And then once it's done, it kicks out of this loop and goes back to the Senior Design, and that's when it does that dance that you saw earlier. This is an example, this is a picture actually of the teach pendant that we use to program the robot. This side of the screen is the Senior Design program. You can see here the list of like commands and registers. And this side is a list of just all registers. So these are PRs or position registers. And we have one for each snap circle. That's where it goes to look at each piece. And then one for each pick place and where it places each piece.
Hi, so I'm Ben. My main portion of the project was the vision system. So the most important part of a vision system with this robot would be the piece lighting. So we have backlighting underneath each piece made of an LED puck light that is usually used under cabinet lightings in the kitchen. And then the acrylic circles that Addison was talking about in the feeder system diffuse the light from that LED underneath so that it doesn't produce a glare in the camera. And then we have each of those lights mounted in a 3D printed fixture underneath the rotary feeder so they stay in the same place, centered under each of those circles. And we have, when we took it to the IM room for Junior Crimson Day to show it off, we had slightly different lighting, so we had an issue with the lights in the ceiling of that room were darker than the room we'd been testing it in. So we had to actually modify and add another light to that, which then illuminated the work surface a little bit better for the box, because it also takes a picture of the box that it's going to assemble the pieces into. And here's the vision process. So the robot positions the camera above each circle one at a time, and then using the snap tool and the geometric pattern matching tool, takes a picture of each part, and it looks something like this top left picture here. So there's a dark piece with a light background, and you can see the edges very clearly, which helps with determining orientation of the part and location of the part within the circle. And the vision system also returns a model ID, so it identifies which piece is in which circle. And then has some error checking for if the piece is flipped upside down or is missing from a circle, which will then abort the program and not put together the puzzle. And this is the calibration grid we use to define a coordinate system. So we place this grid in before we set up for the day and define the coordinate system at the very center of the grid here. So all of the location movements are based off of that coordinate system on the feeder plate itself. And then here's a video of it running. You probably saw it over in the open house if you were there. So this is the same thing. It's going along, taking pictures of each circle, and then determining location and rotation offsets. And then it goes through and picks up the pieces one at a time, starting with the bottom left piece. And it'll always do the same order of the pieces assembly, as explained by Kyle in the program structure. And then when when the puzzle is completed, the prospective student would pull up on the T-handle in the bottom right there and rotate the rotary feeder out to have a complete puzzle. And there's the celebratory dance at the end.
So as talked about before, safety was a key aspect of this project. The amount of interactions and the number of people dealing with this robot made it necessary to have multiple layers of safety. So for this project, we met with Officer of Safety Susan Grimm to perform a safety assessment, as well as looking up a lot of different robotic standards in OSHA and some other sources. And we determined through the safety assessment and this research that some of the biggest safety concerns are interactions with the robot, such as pinch points and people getting hit or entangled with the robot. So one nice piece of software that FANUC has proprietary to all its robots is called Dual Check Safety, or DCS. As you can see over here, DCS is a software that generates a virtual bubble around the robot that can restrict its movement so it can't move outside the bubble. So as you see here, this is a full range of movement that the robot can have. As you see here, DCS has limited that to just a certain area, and here it is limited even more to just a designated work area for parts. So this is the first layer of safety. The second layer of safety that we wanted to use was a dedicated mechanical safety frame as a hard stop so that nobody could reach their hands into the work area. And we decided to use a design with 80/20 and Lexan panels for a couple different reasons. One being cost. There are a lot of options on the market that you can use with sensors and light curtains using lasers to guard the robots, but those are a lot more expensive. And in addition, they take a lot more experience to program themselves, and their setup time is a lot slower than 80/20. So some of the features here you see on this CAD model are some Lexan walls to make it visible for the robot, as well as doors with easy access so that you can get into the robot if something goes wrong. Another example of the DCS you see here is a bubble that was put around the gripper and the camera itself so that those pieces cannot be hit into the walls on the inside of the safety frame and damage the equipment of the robot. So this is the actual frame in real life, and as you can see here, the frame provides an adequate viewing area, and it fits on the current frame used for the robot itself, just for the Robo 301 class, to limit gaps so that nobody can fix their hands inside the robot and become hurt. It also maximizes the available workspace for the robot that has plenty of room for the rotary feeder and plenty of room to assemble the puzzles without having to worry about going in strange moving patterns or hitting the inside of the frame.
So, I worked on the HMI on the project as well as Kyle and Ben, and one of the things that an HMI does is it basically displays the data to you that's going on very visually. So you can see over here there's a screen, a chart at the bottom, some pie charts at the side. It basically shows you, what's going on and, your inputs and outputs, so you can see and more quickly identify what you need to do if you're on a manufacturing floor. So we worked with an on-run HMI for the majority of the project. And it connects via a DD9 cable, which is just the blue cable you plug into the back of your computer. We had to learn some softwares for these things, as well as create a connection cable with the help of Mr. Gillette to plug it into the robot itself. What ended up happening though is we had to contact OnRun because we were having a lot of different problems trying to connect the two and get them to interface, and so that led us to a different solution, which was the panel wizard software. So what we have here is a couple different buttons that show you how to start and stop it, as well as whether the gripper is open or closed. Shows you whether or not the puzzles have been assembled and how many have been assembled for the day, and then a different light that shows if the piece was recognized in each slot or not. It, very visually creates a way for you to see it, and a perspective can come up and press the button and run the robot themselves, as well as get, a little more information that way. What we found through some of the different costs of our project were, the majority of the project was spent on base plate, safety frame, and rotary feeder. Those were accounted for around 80% just by themselves. As you can see here is 42%, 23%, 21% respectively. After that, it drops off to about 6% and goes down from there, as well as the HMI being 0 because it was a generous donation. We also have this Pareto diagram which shows us that, you can see here the cost of the project. It's a cumulative sum of what percentage we've spent on the project so far. So it really jumps up pretty high to 42% for the base plate, and it starts to taper off a little bit as the costs go down and down, which is to simulate, or emulate how the once the design is, the most expensive part of the project, you kind of wean down how much you're spending as the project goes on because you have something in place and you're not ordering as big of parts anymore. We also had the total cost of the project being around $2,941, and the cost of making an aluminum puzzle was $483.80 per wood box due to some cheaper ways we could get it done. We didn't end up spending on that because the engineering department covered that because it was a way to bring in perspectives. Lastly, we took some analysis of Junior Crimson Day. We found that about 8 students really enjoyed the project and said it really was a success from the mechanical engineering department. All of the students really saw that the robotics minor was reflected in the project, which makes sense because we were dealing with a robot in the project. And the project made them interested in attending Grove City, which everyone said they at least agreed or strongly agreed with that, which is really what the goal of the project was. So we consider that a huge success for us for Junior Crimson Day. The last thing we have is future use. So we want to produce and cut out puzzles through the summer. There's different people that will work in the shop, Jim being one of them. And with the wire EDM, a lot of times you can set it and then come back to it once it's done cutting out a puzzle. So we can continually produce those throughout the summer, as well as produce boxes through the summer and, keep those in production. The last thing we want to do is teach students that are younger than us how to keep this going, because this ultimately isn't just a project for right now. It's to go on to show students what they can do if they come to Grove City as a mechanical engineer and what robotics options are offered to them. We just want to say a special thank you to a few people, being Brian Montgomery for some of the donations that he made, Jim Pikes for helping us out a ton in the shop, Mr. Gillette for helping us with the cable, Dr. Allison for leading the project and helping us with that, and the various shop assistants that worked on the project as well. We'd also like to thank you for coming here and listening to our presentation, and we'll now take any questions that you may have.
You said that the grippers have been designed to be replaced quickly. Was there any kind of estimated life expectancy of those? Was it lower than you thought it might have been, that there would be a reason to have them replaced so rapidly?
The initial design was just using plastic grippers from the 3D printer. So that's how I wanted it to be fast, because those were just a temporary measure. So we didn't want to be very invasive when we finally switched to aluminum ones. And then we redesigned it at one point simply for them to work better. So just because we had several iterations, we wanted it to be easy.
Also, for the robotics class in the fall, they'll be using different end-of-arm tooling on the end, so they want to be able to swap out quickly for that.
How many puzzle sets do you expect to make per year? And do you think there are any more economic processes than the wire EDM that you can use for the puzzle sets? I know it's not the robot project, but I'm just curious to know.
I think that, we're planning on making about 150 to 180. Wire EDM, like you're saying, is a costly way to do it, but for us, it kind of creates the most tight tolerance way that we can without, it has to be so precise. The way that we went through making the puzzles, a lot of times one little thing being off with the puzzle would be enough for the robot. It's putting it in the same spot each time. It'd be enough to throw it off and not be able, you'd almost have to make it bigger gaps and it wouldn't look very good. Sometimes that's
So 150.
Yes, sir.
We would like to, maybe in a future iteration of the project, maybe have them look at maybe a more cost-effective manufacturing way to see if maybe it would be possible to outsource these puzzles to somewhere else.
Right.
If they can come up with a new process, which would still work with the robot itself. So.
So when it comes to just the amount of effort put in man hours and woman hours when doing this project, was it something that, did you put in as much work as you thought you were going to do? Did it take a lot longer than you thought it would take? Or just
Ben, do you want that one or do you want me to take that?
There was a lot of hours put in.
We put in a lot of work. Ben especially, he was in there sometimes 6 and 8 hours in a day just working on the robot. He'd be there till pretty late. And with everything that these guys designed and Wyatt included, they did a lot of Creo design work in the first half. that I know that they were up till all hours of the night putting together. I mean, when you looked at our project, everything that we ordered that wasn't made in-house that we could, had to get right, we got right on the first time, which was key because as you saw, we already spent 42%, we spent 80% of our budget in the first half of the year. So, I mean, it's a really commendable job by everybody in the design team that they were able to get everything so down and so square and so perfect. There was a lot of more work put in than I think we originally intended.
Thank you, team. That's very good.